the interaction of Mth coherent state with two-level atom. Outlines, I will talk about introduction, then what is the Mth coherent state, its properties, non-classical properties. Then I will talk about the interaction of this Mth state with the emerging patterns of this interaction and other measurements, and then I will conclude. First, introduction, the coherent state. It's really famous. It's well known in quantum optics field. It is the most or closest quantum state to classical fields. It's called, or so-called, coherent state. It can be defined in different ways. One of the ways it can be defined as the eigen state of the annihilation operator, and it also can be expressed in terms of superposition of number states or photon states. This is its format. Some of its properties, it has a minimum fluctuations. That is the fluctuation of the position and momentum. If multiplied, it will always give 1/16, which is the minimum possible value. And also separately, each one of them, of the two uncertainties, equals quarter for this coherent state. It can be generated from vacuum using the displacement operator. Now, the non-classical features. The coherent state has no non-classical features. It is, as we said, is the closest state, the closest quantum state to classical fields. Non-classical states are important in many areas of quantum information, quantum optics. We have squeezing, entanglement, and many other features that are non-classical, and they are very important in many fields. Many states were proposed to combine non-classical aspects with some features of coherent state. These states, which combine the coherent aspect and non-classical aspect, allow us to study the quantum to classical transition and hence better absorb the wave-like and particle-like natures and other phenomena. For example, to these states, we have different type of superposing two coherent states. Two coherent state alpha and beta can be combined, and we will have non-classical state, an example of that. Truncated coherent state, that is not to go to infinity, or just to go to finite n, capital N, or number state filtered, that is to filter one of these photon states. The photon added subtracted coherent state. We add photon to coherent state or subtract photon. However, most of these states and others either very close to regular coherent state or highly non-classical. So most of these are very close to the regular coherent state, which then no benefit of being so close, or being very non-classical, that is far from the coherent state itself. So we propose the Mth coherent state that is defined to be applying the operator, number operator m times to the coherent state. The number operator is known is like its annihilation and its creation annihilation operator. It's like adding and subtracting photons m times from the coherent state, like adding and subtracting continuously. It can be expressed this way, and the normalization constant in m is given as here. If m equals 0, we return back to CS again, which is a coherent state. Let's see its properties. The photon distribution. The black curve is the regular coherent state. It's just a bosonian distribution. However, the Mth coherent states that we propose with different m's, we see similar shapes to coherent state, but they are shifted, as can be seen. Here we select alpha 4. The distributions are similar to the boson distribution, but with a constant shift, semi-shift. It's not exactly identical. They are not identical, but they are very close to each other. Then we concenter them. We make them all share the same peak by setting alpha of each mth coherent state to have this expression. By let each mth coherent state having its own value of alpha, we can make them share the same peak. So we call this peak representation. This suggests to measure alpha for each mth coherent state differently, but to let the peaks of all distributions at the same position. This is the new barometer. Here they all share the same peaks position. Here we can see here the coherent, and all of them have the same value, which is here is close to 16, 15.49. The benefit of choosing this representation, more than it let them all share the same peak, they also, this number MP, the peak representation, directly or very close directly to indicate the number of photons in the state. So if you know the MP, you know the estimated number to the average number of photons, as the two curves show here. Let's study now the overlapping. Let's see how much this new state, mth coherent state, is close to the coherent state. So we introduce the overlapping, and it shows the two curves are the same, the two plots here the same, but different scales. Here with 30 and here with 140. We see it's asymptotically reached to 1, which means it's very, very close to coherent state, and it goes towards 1 as we increase the number of photons. And as m increases, also we see the values get a little bit far from 1. But eventually all of them get close to 1. Now the minimum uncertainties that we multiply the prediction of the uncertainty of position and momentum. When we said earlier the minimum value, which is 1/16, the black curve is for the current state. It always maintains 1/16, but the mth coherent state in the beginning, it has different values, but eventually and very quickly reaches not exactly reaches, but being very close to the minimum value for different phases. We see the same phenomena. It's almost 40 or more. We see most of the curves reach the minimum uncertainty. All these things tell us that the mth coherent state is very close to coherent state. We also here have another evidence from AHMED function. It shows the distribution of the state in the phase space. Here the coherent state of M0, and here the other mth coherent state. They are very, very close to the coherent state. Now let's see the other part. We saw that the mth coherent state after around MB equals 40 and M less than 10, for example, the coherent state becomes very close to a coherent state. The coherent state hasn't any non-classical properties. So will the mth coherent state, since they are very close to each other, will the mth coherent state be the same, will not have the non-classical property? We will see. We will investigate the sub-Bosonian distribution and squeezing. So we start with sub-bosonian distribution. It refers to photons being more likely separated than the boson distribution that in a phenomena hasn't any classical counterpart in photons. We use the Q-Mendel barometer to study this feature. And it is basically, if it's negative, then the state is non-classical. If it's positive, then the state is super-bosonian. We can't judge it. So let's see what we obtain. The black curve shows the coherent state, which is always 0. That means it's coherent state. It's not negative. It's not non-classical. However, all the mth coherent state are negative, and they are significantly negative even for high values like 200. They are significantly negative. That means they are non-classical. Let's see the squeezing. A state is considered to be squeezed if one of its uncertainty, position, or momentum is less than the minimum value, which is quarter in this case. We can study it using the linear squeezing parameter. If this parameter is negative, then the state is squeezed. And we here see the black curve again is for the coherent state, and the other curves are for mth. And we see very long tail showing the negative values, and they are very significant. Since the maximum negative possible value is -1, we have here reach an M20 minus around -0.6 up to 200 average number of photons. We have significant squeezing in mth coherent state. So the mth coherent state has extreme non-classical properties while having significant similarities with the coherent state. So this itself is interesting. We have a state that being similar to coherent, and as this shows, the overlapping is extreme, while the non-classical are significant as well, non-classical part. Let's go now to this. This study suggests that we see the interaction. What about the interaction with the two-level atom? Will the interaction be exactly as the coherent or what? So here we use the two-level atom model. This is the Hamiltonian of two-level atom. With this part shows the Hamiltonian of the atom. Two states, ground state and excited state, and here the interacted quantized field, which is the light, single mode interacting, and here the interaction term of the Hamiltonian between the field and the atom, and here the Keir medium, which is non-linearity, which we can put at 0 if we wish, or other values, and here the A capital, which is a generalization to the creation and annihilation operators. We study first the inversion, which is seeing the evolution of electrons in the excited state and ground state, the difference between the evolution of the excited state and ground state. In the beginning here, we see in the black curves, we see the time evolution of this inversion for the coherent state. And we interact the atom with the coherent state, we obtain these behaviors for different scenarios, different detuning. When we increase the M1, we see here no difference, almost the same. If M is 10, also mostly the same. Okay, we went very large, then we try 50, for example. We start to see that these packages start to be a little bit different. These fluctuations start to disappear. It's like as the shape start to appear. And we see for different scenarios the same phenomena. Then when we go very high, like 100, we see it very clearly that the peaks are very clear and fluctuations disappear. And here we focus on two examples just to see it clearly. Here the coherent and here the mth, here with 50, m equals 50. And we see how they have similar identity, if we can say, but we see that the shapes are different, the fluctuations are decreased, and other modifications. Here we notice another phenomena. In a certain period between these values for our selected parameters, we see when for the coherent state, it's almost like somehow semi-regular fluctuations or something. However, when we put M10, we see these shapes start to be more regular. And then when M equals 50, we see very nice and regular shape. We see this shape is not clear, and then it's resolved over time. And after it resolved, it come back again to be non-clear. This is also visible in 100, visible in all M between 50 or even lower, 40 probably, to 100. Different shapes are start from unclear, then resolved in the middle. We call this resolution phenomenon. We also could specify which time will appear this phenomenon according to this equation. This is basically, it's a semi-regular pattern being apparent in a specific region as this shape, while after or before this region, this pattern is overlapping. It's like disappear. And here different values for this phenomenon. Then we study the Q-Mendel barometer, which is, we referred to it when we study the Mth Coherent State separately. And here the interaction with the atom. In the beginning of the interaction, we see it here, the black of the coherent state and other M value. We see the different, they mostly have the same interaction way. And when we go to the time of resolution, we see that the coherent part is mostly just fluctuations. However, for M50 or 100, we see again the same phenomena of resolution phenomenon that we talked about earlier. Here is focused. The coherent is just almost random fluctuations, and here are organized for M50 here example and 100. We see squeezing. We see just squeezing in the beginning of the time that we have negative values. But after that, we see just vibrations. But we see, interestingly, that these vibrations have almost the same frequency, but different decay rates. And here in the resolution time, we see almost the resolution disappears that we saw it earlier. All of them are wiggling. And different phase also, each one of them display different decay rate. Finally, the similarity between the similarity between the coherent state and the Mth Coherent state is ambiguous, is clear. Large value of M tend to make the system more periodic. Manipulating the two-level atom by imposing different M values of the M's coherent state, we can manipulate it. As we saw, we can change the properties of the peaks. We can make them wider or taller. The resolution phenomenon might find its way in applications related to encryption or coding messages. If a state is needed to have similar probabilities to the coherent state while being non-classical, this state is a good candidate. Publications regarding this work, it started around 2018 or just actually before it. And then the last one is in 2021, which represents the interaction work. Thank you for listening.